Bohr model depicts the hydrogen atom as an electron surrounding the nucleus in quantized orbits. This model was successful in explaining the observed emission lines from hydrogen. Transitions from higher to lower orbits emit light in quantized wavelengths. Let's take a look at the emission spectra from hydrogen gas. In order to do that, we're going to use this apparatus here, which consists of a high voltage power supply and a glass bulb filled with hydrogen gas. This operates essentially the same way as a neon sign. Turning this on, we immediately see this pink color emitting from the bulb. This pink color is produced from the overlap of all of the different emission lines from hydrogen gas. There's a few different ones, but they're all emitting from the same place, and their colors combined together create this pink. In order to space this out and look at the individual lines, the individual colors that make up this spectra, we're going to use a diffraction grating. Diffraction gratings work a lot like prisms in that they separate light out into its component wavelengths. By placing the diffraction grating between the light source and the camera, it will separate out the light to reveal the spectral lines. Rather than doing this with this small grating here, I have a camera lens that fits onto the camera, so we can do this with a little bit higher resolution. By placing the diffraction grating in front of the lens, we're able to see the individual emission lines. There are 3 prominent emission lines in the visible portion of the spectra: red, blue, and violet. The other lines seen here are artifacts from the emission lamp. Using a device called a spectrometer, we can measure the full spectra from the hydrogen emission lamp. Here we see the 3 lines in the visible spectrum. One at 656 nanometers, one at 486 nanometers, and one at 434 nanometers. These correspond to transitions from higher orbitals into the n = 2 level and form what's known as the Balmer series.